Hello, welcome to another module in this massive open online course. So we are looking at a wireless base station cooperation scenario in which several base stations are cooperating to transmit to a single user or a group of users, alright. So we are looking at this scenario, which is a very practical example in a cellular network, what is termed as base station cooperation, okay. And what happens in base station cooperation is, if you look at it, we described it in the previous module, that is we have k base stations, okay. K is the number of base stations which are cooperating to transmit to m users, okay. And these are the base stations, and these users are typically located in a region where they can receive the signals from the multiple users, such that at the intersection of these various cells. So you have 3 cells, in the intersection you have some of these users, and these can be served by multiple base stations, not just a single base station. So the base stations can cooperate with each other to enhance the signal to noise power ratio at each user, okay. And Hij, this quantity denotes the fading channel coefficient between the ith base station and the jth user, and therefore magnitude Hij square, this is the power gain, okay. And what this means is, if you look at the power received by jth user from the ith base station, so let us say, so we already said, I think, or let us say that now we have another quantity, let us say Pij. Pij is the power transmitted by ith base station to jth user, okay. So Pij equals power transmitted by ith base station to the jth user. So Pij denotes the transmitted power, magnitude Hij square is a power gain, which implies that if I multiply, so this is the transmit power, so if I multiply Pij by magnitude Hij square, now this quantity, this denotes the power received by user j. So this is the power user j from the power received by user j from the ith base station. So this quantity is given by Pij magnitude Hij square, okay, alright. So now what we can look at is, let us look at the total power received by user j, any particular user j, from all the base stations. So to compute the total power at any particular user j, you have to sum the power that is received from all the base stations, and that is given as, so what is the total power of user j? By total power of user j, I mean total power of signal received by user j, that is basically the sum of power from all base stations. From all base stations, and that is basically, you remember the base station index is I, so you have to sum over all I. So I equal to 1 to k, k is the total number of base stations, Pij magnitude Hij square. This is the total power received by user j from all base stations. From all base stations, and now what we will say is, this has to be greater than equal to some quantity Pj tilde. This is the minimum power that is desired by user J. This is the minimum power that is desired by user J. So, the total power at user J received at user J has to be greater than or equal to some quantity Pj tilde, which is the minimum power, alright, the minimum desirable, you can say the minimal desirable signal quality at that particular user. This is known as a QoS constraint or a quality of service constraint for that particular user. Okay, so this constraint is also termed as a QoS or a quality of service constraint. Quality. So, your signal quality has to be such that the received power has to be at least greater than or equal to Pj tilde. So, we will have one quality of service constraint for each user. Remember, we have m such users, therefore, we will have m quality of service constraints. Okay. If I remember correctly, we have m is the number of users. So, therefore, we will have m such quality of service constraints. What are those quality of service constraints? Well, for user 1, remember we must have P I j equal to 1 magnitude h I 1 square I equals 1 to k. This has to be greater than or equal to P 1 tilde, right. This has to be greater than or equal to P 1 tilde. Summation I equal to 1 to k. Now, we can write for user 2 P I 2 magnitude h I 2 square, that is h I 2, remember, is a channel coefficient between base station I and user 2. This has to be greater than or equal to minimum desirable power P 2 tilde of user 2, so on and so forth. You will have summation I equal to 1 to k P I m for the mth user magnitude h I m square greater than or equal to P m tilde. These are the QoS constraints, these are the m QoS constraints. Remember these, what are these? These are the m QoS or quality of service constraints. There is one constraint for each user. There is one constraint for each user, and if you look at each constraint, remember in the powers, this is linear combination, this is a linear combination of the powers, this is of the transform C bar transpose x bar less than or equal to this is of the form A bar transpose x bar is less than or equal to B, okay, where this we are looking at x bar is basically nothing but the powers. So, each of this represents the hyperplane, each constraint represents, you can see each constraint represents a hyperplane. So, this implies, correct, this implies that this is an intersection. I am sorry, each constraint represents a half space, not a hyperplane. I apologize. Each constraint represents a half place because this is a, which means that this is an intersection of half spaces. This is an intersection of half spaces. And implies this, which implies that this is equal to a this is equal to a polyhedron. Remember, that is what we said, an intersection of half spaces and hyperplanes is nothing but a polyhedron, and this is an interesting, very interesting practical application. So, the set of all possible powers which meet the quality of service constraints of these different users in this base station cooperation setup, right, this cooperative multi-point setup, the set of all possible powers lie in a polyhedron, which is obtained as the intersection of the half spaces given above. So, the set of all possible powers. So, this is very important. So, in a practical optimization problem, set of all powers that meet the QoS constraints, these are in a polyhedron, these lie in a polyhedron or a polyhedral region. So, to optimize this powers that are transmitted to the different users by the base station, correct, one has to consider the set of all possible powers that lie inside a polyhedron for this optimization problem. Now, similarly, remember each base station also has a possible power constraint, total power constraint. So, you can consider that also, right. So, now each base station, now looking at it from the perspective of a base station, each base station, so let us look at the base station power constraint. Now, if you look at the base station power constraint, now each base station has a certain maximum power let us call this maximum transmit power as Pi bar. Pi bar equals max transmit power of base station I. This is the maximum transmit power of base station I. Now, what does it mean? That is the power that has to be transmitted, the power that is transmitted to all the users, all the M users by each base station I has to be less than or equal to this quantity P bar of I, because this is the maximum possible transmit power, correct. So, this implies that if I look at any particular base station and sum the power over all users, so I must have Pij transmit, summation of all transmit powers has to be less than or equal to P bar I. And what is this? This is the sum of transmit, total transmit power, total Tx power of base station I to all users, to all M users. In fact, you can say this is total transmit power to all the M users. So, this has to be less than or equal to Pi bar. So, you can write one constraint for each base station. So, what does that mean? You will have j equal to 1 to M P 1 j total transmit power of base station 1 to all users, that is less than or equal to P 1 bar, j equal to 1 to M summation P 2 j total transmit power of base station 2 to all users less than or equal to P 2 bar. So on and so forth, you can write k constraints, one constraint for each base station. So, j equal to 1 to M P k j less than or equal to P k bar. These are, what are these? Well, these are k power constraints. Now, you can see again each is a half space, each is a half, okay, and again you have these k power constraints, each is a half space. So you have the intersection of k half spaces, a finite number of half spaces. So this also represents a polyhedron. Okay, so there is an intersection of k power constraints, one for each user, which is equal to polyhedron. So either you look at the QoS constraints, one for each user, total of intersection of m constraints, m half spaces, that is a polyhedron. And now if you look at the total power constraints of the base station, of each base station, for each base station I, you have a total power constraint. So this is again the intersection of k different half spaces, also polyhedron. So the set of all possible powers such that you meet the total transmit power, the transmit power constraint at each base station, the set of all powers that satisfies this set of constraints is also a polyhedron. So therefore this polyhedron, which basically is a region that is formed by the intersection of either hyperplanes or half spaces, which is a convex region, has significant utility and arises frequently in various optimization problems, especially in the context of signal processing and communication, and this illustrates one such simple application scenario. Alright, so we will stop here and continue in the subsequent modules.